Hello, students, and welcome to our lesson on literal equations. We're going to dive straight into this one with what is a literal equation. Most of you have probably never heard this term before, and to be quite honest with you, even within the math community, we don't use this phrase literal equation all that often because generally we just call it a formula. So that's our first bullet here. A literal equation is also known as a formula. Literal equations or formulas are equations that relate two or more variables. And so essentially what we're going to be doing in this lesson is taking formulas and rewriting them in terms of different variables. So the one we're going to start with here says to consider a equals pi r squared. This formula relates the area, which is a of a circle, to its radius, which is r. So the formula is read that area equals pi times radius squared, okay, where a is the area, r is the radius. In this form, we have the a all by itself, isolated on the left side. So in this form, we say that a is written in terms of r. Now this phrase in terms of, think about what the right side of this equation is, pi r squared. This is one term, okay, because everything's multiplied together, and the terms have r in them. So the only term that describes the area involves an r. So we say that a, which is area, is written in terms of r. Now, terms is plural in this case, but in general, we could have any number of terms. So right now, pi r squared is just one term, but some of our formulas are going to have multiple terms in them. And all we do to describe these formulas is we say what is isolated, and then we say that that thing is written in terms of whatever variables are on the other side. So in this case, you might be a little bit confused because there's a pi there also. So you might want to say that a is written in terms of pi and r, but pi is actually not a variable. Pi is just a number. Okay, it's approximately 3.14, but that is just a number, not a variable. Okay, so now, why do we care about this? This form, a equals pi r squared, is convenient for finding the area of a circle when the radius is known. So if we have a radius, we can just plug straight into that formula for r, and it will give us the area right away. We don't have to do any extra solving steps. But let's say we were in the opposite scenario. Let's say we know what the area is, and we want to find out what the radius is. So our next formula down there says r equals the square root of a divided by pi. In this class, we don't actually cover how to solve this one, or at least not yet. It's coming up later. But what we do to get r by itself is we use inverse operations. And in this case, the inverse operations we needed to use was divide both sides by pi, and then take the square root of both sides. Don't worry about that part yet, though. We just care about how this formula looks right now. So in this form, r equals the square root of a over pi. This is the same formula, but now we have r written in terms of a, where r is isolated, but the terms on the other side have a in them. We could also say that this formula has been solved for r, which really just means that we got r isolated. This form is convenient for finding the radius of a circle when the area is already known. So it's the exact opposite scenario of before. And in general, we can solve literal equations for specific variables to fit whatever needs of the scenarios we have. So what we're going to be doing in this lesson is I'm going to give you a whole bunch of seemingly random formulas, and we're going to practice solving for specific variables. But then at the end, I'm going to give us an application where we have an actual reason to solve. And generally speaking, we want to solve a literal equation when we have to do the same thing more than once. So imagine that I have a whole bunch of radii, so the radius of a whole bunch of different circles, and I want to calculate all the areas. I would not want to use the second equation that says r equals square root a over pi, because I would have to plug in r and then solve for a over and over and over again every single time I want to plug in a new radius. So instead, I can use the top formula, a equals pi r squared, and then I can just plug r in directly. So when I plug in the first r, it'll give me a right away. When I plug in the second r, it'll again give me a right away. I don't have to resolve. So essentially, we solve literal equations mostly for the purpose of being able to reuse the result. So if I wanted to find a whole bunch of areas, I would solve for area first and then just reuse that formula over and over and over again. All right, so now, how do we do this? Solving a literal equation for a specific variable requires getting that variable isolated, which is what solving has always meant for us, is get that thing isolated. To do so, we're going to use the exact same processes and inverse operations that we use to solve equations. So for example, in each instance below, we would use the same exact steps to solve for x. So the left one is what we're going to do first. It says 3x plus 1 equals 10. We're going to use inverse operations to get x isolated. So I'm going to subtract 1 from both sides, just like I would for any other two-step equation. Use the additive inverse first to get 3x equals 9. And then I'm going to divide both sides by 3 to be left with x is equal to 3. Not too bad at all. Now we're going to apply that exact same logic to ax plus b equals c. So notice that the 3 from the first one is the a in the second one. This plus 1 is the b, and this 10 is the c. So it lines up letter by letter, number by number, but we don't actually know what a, b, and c are in the second version. But we're going to do the exact same steps. In the first one, we use the additive inverse first. So in this one, we're going to do that same thing. We're going to subtract b from both sides to get that b to the other side of the equation. So we now have ax on the left. The b's cancel each other to give us the additive identity of 0. And then on the right side, this is where things feel a little bit different. I can't actually do c minus b because I don't know what the numbers are. So these are not like terms. Okay, whenever we have terms that are not alike, meaning they are different variables with different powers, we just write them as we see them currently. So c minus b does not get put together, it just stays c minus b. So notice when I wrote the minus b, I wrote it slightly to the side of the c because I'm not actually subtracting them from each other. I am keeping them as separated terms. All right, and then now we would use the multiplicative inverse. We're going to divide both sides by this a to get x by itself. On the left side, we just get x. And on the right side, again, because we don't know what c, b, and a are, we leave it as c minus b all divided by a. And that would be that formula, ax plus b equals c, solved for x. So now let's see how it's the same. We know from the first problem that we had a equals 3, b equals 1, and c equals 10. So if I were to use those numbers in that second version, if I plug in c is 10, b is 1, so 10 minus 1 on top, and a is 3, so 3 on bottom. This gives me 9 over 3, which is once again 3. And so by solving for x equals c minus b over a, I have actually solved every single problem that's in this form, ax plus b equals c. All I have to do to get to every single answer now for anything that looks like ax plus b equals c is plug in a, b, and c to this c minus b over a formula, and it will give me x right away. I don't have to redo any of those solving steps. All right, now we're going to see a bunch of examples of different formulas we can solve. So number 1 says solve for r, c equals 2 pi r. Think of this instead of c equals 2 pi r as just c equals 6r. If it was just a 6 there, we would divide both sides by 6, and we would say that c over 6 is equal to r, and we'd be done. Just one step if it was a 6 there. This is the same problem. The only difference is instead of the number 6, I have the number 2 pi. But notice I said number. 2 times pi is just a number. So we can divide by it just like I could divide by 6. So on both sides of this equation, I'm going to divide by 2 pi. When I simplify this now, the left side, nothing changes. Just c over 2 pi. There's nothing to simplify there. But on the right side, notice the 2 pi on top and the 2 pi on bottom cancel each other. So we're just left with r. So c over 2 pi equals r is this same formula solved for r. Where in case you recognize it, c equals 2 pi r was the circumference of a circle based on its radius. So we started with circumference in terms of radius, and we ended with radius in terms of circumference. So if you gave me a whole bunch of different circumferences, I could use this formula where I just divide by 2 pi to get all the radii of those circles. All right, number 2 is a little bit more general, where we have actual words in our equation. It says to solve for time, and we have that distance equals rate times time. So what we're going to do is just divide both sides by rate. Okay, if we wanted to, we could write this as d equals rt, but there's nothing wrong with leaving it as words. Okay, rate, when we plug in for it, would just be a number. So right now it's a variable, but when we actually have numbers, it would just be a number there. So if we had a number times time and we want to get time isolated, we just divide by whatever that number is. We do the multiplicative inverse. Okay, so the opposite of multiplying by rate is dividing by rate. I do that on both sides. The left becomes distance divided by rate, and the right side is just time because the rates canceled out. So we now have that time is written in terms of distance and rate. So in this case, we have two variables. Time is written in terms of distance and rate. In the original part, where we had distance equals rate times time, we would have said that distance is written in terms of rate and time. All right, moving on to the next page. For number 3, we have solve for h, where a equals 1/2 bh. This is the formula for the area of a triangle, where area equals 1/2 base times height. Okay, what we're going to do here to get h isolated is one step for the first one, and then I'm going to do it in 2 steps in case the first one doesn't click too well. So this is exactly the same as what we did in number 1, where I divided both sides by 2 pi to get the r by itself. Here, we have 1/2 b attached to that h, so we're just going to divide both sides by 1/2 b. So 1/2 b over there, and a 1/2 b on the other side. The left side, a divided by 1/2 b, a over b, nothing crazy happens. But the 1/2 on bottom, remember, whenever we divide by a fraction, we multiply by the reciprocal. So that's going to become a 2 on top. So I end up with h is equal to 2a over b. All right, so now I said I'm going to do this one twice because for a lot of us, that 1/2 becoming a 2 on top might not click. So let's do it a slightly different way. If I restart with a equals 1/2 bh, we learned how to clear fractions in a previous lesson. So that's going to be my first step this time. I'm going to clear the 1/2 fraction by multiplying everything by 2. This 2 distributes to the a and also to the 1/2. But notice it only multiplies by the 1/2 on the right side because 1/2 b times h is all one term. So I only multiply the 2 to the front. After this multiplication, I get 2a equals bh because 1/2 times 2 just gave me 1 there, and I don't need to write the 1 for multiplication. So now that I have 2a equals bh, I can divide both sides by b and get to the answer we had doing it the first way, which is 2a over b is equal to h. So I did it in 2 steps the second time, 1 step the first time, but mathematically perfectly equivalent either way. Number 4, we have solve for w, where p equals 2l plus 2w. This is the area, or sorry, the perimeter of a rectangle, where we have perimeter equals 2 length plus 2 width. Okay, so this is just adding up all 4 sides of a rectangle. And all we have to do to get w isolated here is move the 2l to the other side and then divide both sides by 2. So we have 2 steps this time. This is a 2-step equation where we first are going to subtract 2l from both sides. Now this part, the way you write it, gets a little bit wonky because when I subtract 2l from the right, I just write it directly underneath the other 2l. But when I do it on the left, p and negative 2l are not like terms, so I actually write the 2l a little bit to the side. So now notice, if I bring everything down, the left side would be 2l plus p, where those are separated, and the right side, the 2l's cancel, and I just have 2w left. Okay, now here's the thing. Whenever we have subtraction of a variable term like this, we prefer to write it in the back. So although mathematically what I just wrote is perfectly fine, okay, I'm going to rewrite the left side as p minus 2l. Okay, and the only reason I'm doing that is we prefer in mathematics that we don't have a negative sign at the start of the thing we're writing. So by writing it as p minus 2l, we only had to use one operation here, just this minus sign. But by writing negative 2l plus p, I have a negative sign and an addition symbol. So it's actually more writing if I write it as negative 2l plus p. Now, this is kind of nitpicky, but this is a commonly believed, or at least commonly followed, rule in math, is that when you have the option to write it in a more convenient way, you do it. So negative 2l plus p and p minus 2l are exactly the same thing, but p minus 2l is better. All right, now that being said, we have one more step, which is to divide both sides by 2 to get w all alone. When I do this, I end up with p minus 2l is equal to w. I'm going to write this down on the side here because I kind of ran out of space. P minus 2l over 2 is equal to w. So now we have p minus 2l over 2 equals w. That is perfectly fine, perfectly acceptable. And if you answered that way, I would not complain on a test. However, some mathematicians are going to call you out and say that this isn't quite simplified enough. All right, when you have addition or subtraction on top of a fraction, we can distribute the 2 on bottom to both terms on top. So I can rewrite p minus 2l over 2 as p over 2, where I divide the first term by 2, and then minus 2l over 2. So I can rewrite it as p over 2 minus 2l over 2, where I just split the fraction into two pieces. Notice those fractions I just split it into have a common denominator. So if I put them back together, it gives me exactly what I had before, p minus 2l over 2. But now I can simplify this fraction a little bit because p over 2 might not change, but 2l over 2 is just 1l. And so the best way you can write this answer is that w equals p over 2 minus l. Now, I want to make it clear that technically speaking, it was fine the way I wrote it at the top. P minus 2l over 2 equals w is correct. But the bottom way, p over 2 minus l equals w, is the best way to write this one. Okay, it's going to require the least input by the user. All right, number 5. We have to solve for x where 3x plus 2y equals 10. Okay, getting x alone is going to require us using both inverses, additive and multiplicative. I'm going to subtract 2y from both sides first. Where notice on the right side of this equation, when I write the 2y, I don't write it directly under the 10. I write it slightly to the side to remind myself that these are not like terms. I'm going to write 10 minus 2y in the next step because I cannot combine those. They are not like terms. So now that we have 3x equals 10 minus 2y, I divide both sides by 3. And I'm left with x is equal to 10 minus 2y all over 3. You could do the same thing we did in the previous problem and write this answer as 10 over 3 minus 2/3 y. And so that is mathematically equivalent, 10 over 3 minus 2/3 y. Okay, that is the same thing. In this case, though, I would argue that the first way is actually better. Okay, 10 minus 2y over 3, in my opinion, is actually better because notice that they both represent the same thing, but in the second version, nothing's simplified here. 10 over 3 and 2 over 3 both stayed unsimplified. So when you're in a situation that the fraction cannot be simplified like this, it's actually better to leave it as one fraction. In the previous problem, though, number 4, 2l over 2 simplified to just be l, so it was better to break it into two pieces because one of those pieces became extra simple. So it's all based on context. If things simplify, then simplify them. But if they don't, then it's better to leave it as one fraction. All right, number 6, we're going to do the exact opposite of what we just did. We want to solve for y this time instead of x, and it says 4x minus 3y equals 12. So the process is the same, we're just trying to get a different letter isolated. So in this case, I'm going to subtract 4x from both sides. Where again, on the right side, when I subtract that 4x, I write it off to the side of the 12 to remind myself they are not like terms. So I have negative 3y equals 12 minus 4x. Now I just divide everything by negative 3, where notice that when I do this division, the entire right side is over -3, not just one term. It's the entire side because we have to distribute that -3 to everywhere. When we simplify this, -3y over -3 is just 1y. And on the right side, we have 12 minus 4x over -3. So now what's the problem with that one? It is not good notation to leave your answer with the denominator being negative. So although technically speaking, what we just wrote there is okay, this one is going to be better if we rewrite it with the negative on top. Okay, and we can actually do that because some things are going to simplify here. If we break it into pieces, that negative will move just by us doing the division. So watch what happens if I split it into two fractions here. I can write 12 over -3 minus 4x over -3, where notice both denominators are a -3. But when I simplify this now, 12 over -3 is just -4. And then for the second term, we have a negative and a negative on bottom. So -4x is technically on top, -3 is on bottom. Those are going to cancel each other out to make a positive 4 over 3x. Okay, where that 4/3 is next to the x. All right, so now you're thinking, wait, that answer is not good enough because you said don't put the negative sign in front. That's what I told you up here with -2l plus p. We preferred p minus 2l. Same deal down here. -4 plus 4/3 x. It is better to write it as 4 over 3x minus 4. So we have y equals 4 over 3x minus 4 is going to be our final solution there. Now, 12 minus 4x over -3, technically correct, but it is not the best way to write it. Okay, instead, we want to get that negative out of the denominator, and 4/3 x minus 4 is a much better way to hand this formula off to someone. Number 7, we have y equals 27 minus 1/4 times w minus x. So we have a fraction here, and we have three different variables, where x, the thing we're solving for, is within those parentheses. So what we need to do is get it out of the parentheses. We have two options. We can either distribute this -1/4 into the parentheses to get -1/4 w plus 1/4 x, and then continue solving for there. Or we learned how to clear fractions. If you recall in number 3, I cleared the fraction of 1/2. And that will make it so we don't have to deal with these fractions anymore. So in my opinion, that's going to be the better method here. I want to get rid of that 1/4 so I don't have to deal with any fractions. So I'm going to multiply the entire equation by the multiplicative inverse of 1/4, which is just 4, or 4 over 1. And when I do that, this 4 is going to distribute to the y, to the 27, and to the 1/4. Notice it doesn't go to the w minus x because 1/4 times w minus x is all one term. Okay, when I do this, I get 4y equals 27 times 4 is 108. And then minus 1/4 times 4 is just 1. So I can write a -1 there, but I technically don't need that 1. And then I still have w minus x that was unaffected. All right, so I wrote that -1 in front of the w minus x to show you that 1/4 times 4 became that 1, but I'm actually going to delete that -1 now because it's not good notation to have a 1 in front of parentheses there. It's not wrong, but it serves no purpose for us. All right, so now we still need to get x out of the parentheses. We got rid of the fraction, but x is still buried in parentheses. So we are now going to distribute this negative sign to the w and the negative x, which will give us minus w plus x. So we now have 4y equals 108 minus w plus x. All we have left to do now to get x isolated is move the 108 minus w to the other side. We could do it one term at a time. I could subtract 108 from both sides and then add w to both sides, but we can actually do it all in one step. Minus 108 and plus w. Notice on the right side, those are going to cancel each other out. And on the left side, I just put the same thing in there. Minus 108 plus w. Or again, the right side, everything cancels out except for I'm left with this x. On the left side now, I have to write down -108 plus w plus 4y. but that is not the best way to write it. Okay, we want to have a negative sign not be in front. We prefer to not have that negative sign in front when there's multiple terms and some are positive. So instead of negative 108 plus w plus 4y, I'm going to go ahead and put the 4y in the front. So it's going to say 4y minus 108 plus w. All right. So that is the way I'm going to choose to answer this one, is that x equals 4y minus 108 plus w. You could also rewrite it again as x equals 4y plus w minus 108 in that order. And that would be arguably better because the constant term is at the end, which tends to be the better notation, is to put the constant at the end, especially if the constant is the negative term. But both answers, 4y minus 108 plus w and 4y plus w minus 108, both perfectly acceptable for me. All right, number 8, we're going to solve for x, where a over x equals b over c. Notice we have a proportion here, so we're going to cross multiply. X times b just gives me xb. And on the other side, a times c just gives me ac. Nothing to really do there because they're just variables multiplied together. We want to get x by itself, so we're going to go ahead and divide both sides by b to get that x isolated. On the left side, we just have x, and on the right side, nothing to simplify there, just ac over b. So that one ends up being pretty easy once you do that cross multiplication. Then all we had to do was divide by b on both sides. All right, so now a fun application where this is one I've used very, very recently in my real life. So I actually wrote this problem after something that was happening to me, so very applicable. We have that the cost of a home installation project can be modeled by the total cost is equal to the materials plus the labor rate times the hours. So usually we would just say that cost equals materials plus labor. But when we say plus labor, really we mean the labor rate times the number of hours. Okay, but together, when you multiply that, that gives you the total cost of the labor. All right, so now a homeowner gets 2 quotes for installing new windows. And when I say a homeowner, I mean me. So again, real life here. A company, let's call it company A, quotes a total of $2,400, which includes $1,500 in materials, and they estimate the job will take 12 hours. Company B quotes a little bit more, $2,650, but they say it's only $1,300 in materials, and they think the job will only take 10 hours. So the question I have for you is, how much is each company charging per hour of labor? So we want to solve for labor rate. Now, in this scenario, I only wrote down company A and company B, but I want you to know in my real life, I got quotes from about 6 different companies. So instead of it only being 2, imagine there was 6 here. I would not want to have to use this total cost formula to solve for labor rate over and over and over again 6 different times. So instead, what we can do is solve the formula for labor rate and then just plug in the variables we're given. So what we're going to do is take this formula down below where I'm going to simplify it a little bit. I'm going to say that total, so instead of cost, I'm just going to write total. Total is equal to materials plus, and I'm just going to call it rate times hours. So I'm simplifying the wording just a little bit, so that way each variable is only one word, where I have total equals materials plus rate times hours. So now what I want to solve for is the rate, because I'm trying to figure out how much is each company charging per hour of labor. So that is the rate. So in order to get the rate by itself, I'm going to first subtract materials from both sides. Okay, using the additive inverse of the materials here. After doing that, I end up with the left side is total minus materials. And the right side of this equation is rate multiplied by hours. All right, so now we want to get rate by itself. So we're going to divide both sides by hours. And then we will have our new formula. Oops. So this simplifies to be the left side is total minus materials divided by hours. And the right side, the hours cancel, so we just have rate. And remember, when I write rate, that represents the rate for the labor. So specifically the labor rate. All right, so now we did the hard part. Okay, we isolated the rate. So now we're going to use this to compare company A to company B. We want to know how much each company is charging. And so I can use my formula for each company to say that rate is equal to, in both cases, and I'm just going to write the numbers that I have from my explanation up top. So we're going to set up a fraction for each because our formula here is total minus materials over hours. And I'm just going to plug in the three different numbers. I'm going to plug in the total, the materials, and the hours to each formula. So for company A, we have that the total is $2,400. So I'm going to put 2,400 on top. We have that the materials is 1,500. So from that 2,400, I'm going to subtract 1,500. And then we have that the hours is 12. So I'm going to put 12 on bottom. When we simplify this, 2,400 minus 1,500 is 900. So we have 900 over 12. You're more than welcome to simplify that fraction however you want. In my head, I look at it and I say, well, I know 912 are both divisible by 3. So in my head, I go, okay, let's simplify to 300 over 4. And then I know 300 is divisible by 4 because the last two digits are divisible by 4. So I just actually divide now and get $75 as my answer. Where it's dollars because it's dollars per hour of labor is what that labor rate represents. So company A is charging $75 per hour. We also could have done that, of course, on a calculator, just 900 over 12. But I wanted to be a little special and you do it using the fractions because we learned them and it's good math. And don't pull out a lawnmower to mow one blade of grass. All right, next rate for company B, we have a total of 2,650. So I'll put that on top first. And then we have a materials cost of 1,300. So minus 1,300. And then we have an estimated time of 10 hours. So when we simplify this, 2,650 minus 1,300 is 1,350, and the bottom is 10. Dividing by 10 is nice and easy because you just cancel out a 0 from the top, move the decimal place over once. So this gives us $135, and again, this is per hour. So we found both rates. Company A is charging $75 per hour, and company B is charging $135 per hour. So now notice that it's implied by this problem that you're getting the same windows. Okay, so not only is company B charging you more money per hour, but they're suggesting that the materials will be less expensive and it'll take them less time. So now they might be right. This might be a valid quote, but what this sort of suggests to me is that they value themselves, their labor, quite highly because they're charging so much more per hour. And they think that they can do it with less material costs, meaning probably cheaper materials, and that they can do it faster. So one possibility is that this company is just better and they're able to get you a better price on the materials and they're able to do the work more efficiently. So that's why it takes less time. And so they're charging you more per hour because they're more efficient. Maybe they are actually a better company. But on the flip side of it, company A is charging you more for the materials, so it's likely higher quality materials, and they're telling you it's going to take longer, which means they probably plan to take their time and actually do it right. So company A ends up being cheaper overall, and to me, it's suggested that it's because they're going to do a better job. They're going to take their time, they're going to do it right, and they're going to charge you less money per hour because they're not trying to rip you off. Now, again, there's a lot more to comparing things in real life than this. And I ended up actually not going with either of these companies, A or B, that I took these numbers from, because I found a different company who I just liked better. When I talked to them, they made me feel as though they were going to do a much better job. But you need to be able to compare rates like this. When you go, for instance, to let's say replace your AC, there's the cost of the AC unit, and then there's all the other materials and labor that they're going to charge you. And if you don't break the numbers down like this, they're going to try to charge you $1,000 per hour to install something. because they assume that you don't know how to do the math and you can't point out to them, hey, you're ripping me off. I'm not going to pay you that. So by being able to do this, instead of negotiating the cost of the unit, the air conditioning unit, you can negotiate how much you're paying them to do the work per hour. Because the unit might just cost what it costs, but the per hour rate is always negotiable. All right, so hopefully in your real life, this is going to help you out a little bit. Always, 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 if you're paying someone to do a job for you, calculate how much they're charging you per hour. And that's going to tell you a lot about if they are trying to give you a good deal or not. All right, that's all I got for you in this one. And remember, the key here is we solve literal equations to fit the needs of different scenarios. So this is just one example of a scenario, but there is countless, countless other ones we could encounter in real life. And hopefully now you'll be a little bit more prepared for them.